Alright, so this is our function in all of its pixelated glory. We have x times e to the 1 minus x. The first part of the question is asking when f is increasing. Now to do this we need to take the first derivative. And when we want to take the first derivative of this expression, we need to apply the product rule, which is shown to the left. It's the first times the derivative of the second plus the derivative of the first times the second. And we can see after we take the first derivative, we can pull out an e to the 1 minus x from this expression, and we get that the first derivative is equal to e to the 1 minus x times 1 minus x. Next, we want to find the critical value, and we do this by setting the first derivative equal to 0. When we do this, we see that e to the 1 minus x is never quite equal to 0. You can see that by looking at the graph of e to the 1 minus x, which is to the left. Therefore, we only want to analyze the second part, the 1 minus x. And when we solve for x, we find that there's a critical value at x equals 1. Next, we want to apply the test for increasing decreasing. So we do this by finding the intervals that we want to analyze. And the first interval is from negative infinity to 1. The second is from 1 to infinity. Next, we want to evaluate the sign of f prime of x on these intervals. So we can choose any value from negative infinity to 1. Here I chose 0, so f of 0 turns out to be e, which is positive and greater than 0. Next, we want to evaluate f prime of 2, which turns out to be negative 1 over e, which is less than 0. The conclusions that we can draw from this are that f is increasing on the interval negative infinity to 1, and f is decreasing on the interval 1 to infinity. Next, we're asked to find the range of f. And when I'm asked to find the range of something, I usually question what happens as x approaches infinity and as x approaches negative infinity. So we're going to take the limit as x approaches infinity of x times e to the 1 minus x. And this can be written as the limit as x approaches infinity of x times e divided by e to the x, which is equal to infinity over infinity, which is one of the indeterminate forms. So now we can apply L'Hopital's rule. Take the derivative of the top and the bottom with respect to x, and we get the limit as x approaches infinity of e over e to the x, which is equal to 0. Next, we want to find the limit as x approaches negative infinity of x times e to the 1 minus x. And this is equal to negative infinity times infinity, since x just turns into negative infinity, and e to the 1 minus negative infinity is e to the positive infinity, which is a very large positive number, which is infinity. So negative infinity times positive infinity is negative infinity. And we find that the maximum value, f of 1, is equal to 1 times e to the 0, which is 1. So our answer to part B is the range of the function is from negative infinity to 1 with a closed bracket on 1. For the next part, we want to take the second derivative. Now we know that f prime of x is equal to e to the 1 minus x times e to the 1 minus x. But we can simplify this by saying that it's equal to e to 1 minus x minus f of x, our original function. And this makes taking the second derivative a little easier. For when we take the second derivative, we get negative e to the 1 minus x minus f prime of x, and we could just sub in what we know f prime of x to be, and simplify from there. Part C asks us to find a point of inflection. So here we have to set the second derivative, which is e to the 1 minus x times x minus 2 equal to 0. Once again, e to the 1 minus x will never be equal to 0, so we only have to analyze x minus 2. When we solve for x, we find that there is a possible point of inflection when x is equal to 2. To verify that there is a point of inflection when x is equal to 2, we need to apply the test for concavity. So we have to check the concavity of the function on the interval from negative infinity to 2, and on the interval from 2 to positive infinity. So we have to choose a point and then just evaluate the sign of the second derivative at that point. So for the first interval, we can say the second derivative of 1 is equal to negative 1, which is less than 0. For the interval from 2 to positive infinity, we can choose 3 and say that the second derivative when x is equal to 3 is equal to 1 divided by e squared, which is greater than 0. So therefore, on the interval from negative infinity to 2, the function is concave down, and on the interval from 2 to positive infinity, the function is concave up. and therefore we verified that an inflection point exists when x is equal to 2. Finally, we're asked to draw the function based on parts a, b, and c. So in this graph, you can see that on the interval from negative infinity to 1, when x is equal to negative infinity to 1, we see that the function is increasing. And when x is equal to 1, we can see that there is a maximum value at that point. And when x is equal to 2, there's a point of inflection. The concavity shifts from concave down to concave up. Last question. How many molecules are in a bowl of guacamole? Avocado's number.